Hi, this is Srikant, Assistant Professor of Triple Department. In this session, I am discussing question bank problems on Module 2, Network Theorems and Three-Phase Voltages. Here, the question is, what is the necessity of interconnection windings in three-phase supply? And what is the correlation of star and delta connections in three-phase supply systems? The major necessity of interconnection windings in three-phase supply is when we place the three-phase windings together, the size is going to be small, because whenever we are placing three-phase windings together, the size required for a particular machine or for a particular transformer or for particular any of the electrical equipment, the size will be less. And whenever we are having three-phase supply, we are going to get the constant output power, because we are going to have three-phase voltages and three-phase currents, which will provide us some constant output power. And whenever we are having three-phase supply, three-phase connections, either it may be star or delta, which will provide us the easy parallel operation. That is nothing but every line is going to have two lines. The two lines is going to operate parallelly, which will provide us more current, or which will transmit or generate more power by using this parallel operation of the system. And whenever we are having this three-phase system, we are going to have the reliability of the system will increase. So it will have a very good reliability as compared with the single phase systems. And interconnection of systems is possible in star and delta. We can get the interconnection of systems easily either in star or delta. And there is a phase relationship between each phase is 120 degrees displacement, either in star or delta connection system. And this is the star connected three phase system. Here we are having three phases: R phase winding and B phase winding and Y phase winding, which is connected to a neutral point N. And here this is the phase current and this is the line current. The between the winding and neutral, whatever the voltage which we are having, that voltage is the phase voltage. Between the line to line, whatever the voltage we are having, that is line voltage. Here VR is equals to V. VRN is equals to VBN is equals to VYN, which is equals to V phase voltage, where VRB is equals to VBY is equals to VYR, which is equals to V line to line voltage. And here we are having the phase voltage phase current is in the same line of line current. So the line current is equals to phase current in the star connected system. Whereas for phase voltage, V phase is equals to V phase is equals to line to line voltage by root 3. This is the V phase voltage across the star connected system. Now when we go with delta connected system, here also VR, VY, VB. Here there is no neutral, is equals to V phase. And V line is between VRY or VBR or VYB between the lines. But here VRY is nothing but VR because across the each phase. So here the line voltage is equals to phase voltage. Whereas here the currents are going to be divided. So the phase current is equals to line current by root 3. Line current by root 3. So these are the line and phase relationship between the star and delta connected systems. Now write the voltage and current relationships in a three-phase star connected supply. Also write the expressions for PQS and power factor. Here VRN is equals to VBN is equals to VYN, which is equals to V phase. VRB is equals to VBY is equals to VYR is equals to V line to line voltage. So here V phase voltage is equals to V line to line by root 3. V line to line by root 3. That is the V phase voltage. And IL is equals to I phase. Line current is equals to phase current in the star connected system. Now here active power P is equals to root 3 into VL IL cos phi, because when the voltage and current is multiplied with the power factor, that is nothing but a active power. Whereas Q is equals to root 3 VL IL sin phi. This is the reactive power. And S is equals to root 3 into VL IL. This is called apparent power. So these are the three different powers which we are going to have: active power, reactive power, and apparent power. And power factor is the nothing but it is the cosine value of phase angle difference between the voltage and current, which is equals to cos phi. We can write it as cos phi is equals to P by root 3 into VL IL. Now let us take the circuit with three loads and each of resistance 30 ohms are connected in star to a 415 volts three phase supply. determine the system phase voltage, the phase current, and the line current. Here, the load, three phase load, which is connected to a 415 volts three phase supply. So, here let us consider a three phase star connected system. It is connected to the load, here the load is of resistive type, which is of 30 ohms, 30 ohms, 30 ohms. Here 415 volts is the line to line voltage. 415 volts is the line to line voltage. Now we need to determine the system phase voltage. System phase voltage Vs phase is equals to V line to line by root 3, which is equals to 415 by root 3, which will gives us 240 volts. And the phase current is equals to line current because it is a star connected system. I phase is equals to IL, that is equals to Vs phase by resistance, that is equals to 240 by 30. So 8 amperes I phase. And the line current IL is equals to I phase, which is equals to 8 amperes. These are the three parameters which we have calculated: phase voltage, phase current, and the line current. The next one is write the voltage and current relationship in three phase delta connected supply. Also write the expressions for active power, reactive power, apparent power, and power factor. Here in delta connected system, the phase voltage is equals to line voltage and phase current is equals to line current by root 3. Line current by root 3. So all the currents across the phases will be equals to IL by root 3. So here VR is equals to Vy is equals to Vb is equals to VL, and IR is equals to Iy is equals to Ib is equals to IL. IL by root 3. And the power, active power P is equals to root 3 into VL IL into power factor, that is cos phi. This is called the active power, and this is the power which we are going to use in our AC supply or whatever the components which we are going to use. This will take the active power and will be utilized the complete active power. And Q is equals to root 3 VL IL sin phi. This is called reactive power. This is the power which we are going to have because of the reactive components. where S is equals to root 3 into VL IL. This is the actual power, apparent power. Where S is equals to P plus JQ. This is the apparent power equation. Now power factor is equals to power factor is equals to cosine value of phase angle difference between the voltage and current, that is equals to P by root 3 into VL IL. This is the power factor equation for the three phase supply. Now let us take the problem. A 415 volts three phase AC motor has a power output of 12.75 kilowatts and operates at a power factor of 0.77, lagging with an efficiency of 85%. If the motor is delta connected, determine the power input, the line current and the phase current. So here V line to line RMS value is equals to 415 volts and the output power, which is given as 12.75 kilowatts, and power factor is equals to 0.77. Power factor will not have any units and efficiency is given as 0.85 or 85%. So here motor is delta connected. Motor is delta connected. Motor is delta connected. We need to calculate. The first one is power input. Power input. So efficiency is equals to output power by input power. Efficiency is equals to output power by input power, where output power is equals to efficiency is 85%, 85 by 100, and here the output power is 12.75 kilowatts divided by input power we need to calculate, where input power is equals to 12.75 into 100 by 85, that is 15 kilowatts. This is the input power. Now we need to calculate what is the line current and phase current. So the next one is the line current B. The next bit, line current, which we need to calculate. Line current is equals to, here the motor is delta connected, so the line voltage is equals to phase voltage. Line current we need to calculate. So here the line voltage is equals to phase voltage because it is delta connected system. So VL is equals to V phase. So line current is equals to V line by root 3 into line current is equals to output sorry input power by, because we don't have the other parameters, so from the input power only we can calculate the line current. Input power divided by root 3 into VL into cos phi. Here input power which we have got it as 15 kilowatts, 15 into 10 cube divided by root 3 into VL is 415 into cos phi value is 0.77, which is equals to 27.10 amperes. This is the line current which we are going to get. And the next one is phase current. We need to calculate. Phase current is equals to, because it is delta connected system, I phase is equals to IL by root 3, which is equals to 27.10 by root 3, which is equals to 15.65 amperes. This is the phase current. So these are the phase current and line current and input power calculations for the given problem. So these are the different problems which we have discussed on the three phase windings. One is star to delta, star and delta combinations, and with star what are the equations for voltage, current and power equations. And then we have also calculated the power factors for different conditions, and also we have calculated input power and line current and phase current for star connected and delta connected systems. In this session we have discussed the question bank problems on network theorems and three phase circuits. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.